Okay, you guys, this is a kind of large section, and yet it's actually one of my least favorite sections. So it's a lot of kind of memorization. We will use this a little bit. We're really just defining and kind of exploring 4 different segments and triangles, and then their points of concurrency. So for each of these 4 segments we're going to talk about, all 3 of their versions that we will draw in a single triangle will meet. So for example, if we're talking about angle bisectors, that's one of the things we're talking about. All 3 angle bisectors meet at the same point, which is interesting. So we call that the point of concurrency. And just if you think about that, what that means, right? Concurrency, that means together or with, occur. So that literally means they occur together. So it's saying, like, for example, like 3 or 4 friends all happen to bump into each other at the same time at the same store or something. You're like, what? No, you're here and you're here? It's not just where one thing meets another. Like, that happens all the time. Any 2 lines that aren't parallel will intersect. The cool part, though, is that the 3rd angle bisector will actually occur at the exact same point. Like, the chances of it hitting that one point, super slim, and yet 100% of the time in a triangle they meet. That is pretty cool. So that's called a point of concurrency, and that's what we're going to be talking about here. Each of these points of concurrency kind of has like a superpower, and then the book problems are pretty straightforward. They're like, use this superpower, apply it to this problem, and do algebra. And then we do some interesting proofs with congruent triangles and CPCTC. Okay, so I got to give it away. I'm like, this is not my favorite section. It's not a very useful section or lesson where we're not going to use this in the future, really. It's kind of a one-off where we get through it and kind of toss it. A few of the items come up a little bit, but let's hit it. All right, so here's a table that just has everything. I just threw it at you all at once. I will just kind of walk through it. No, I'm not going to walk through it. Here's the table. You could like save this, print it. I have the PDF notes all attached, but I'll walk through each of these one at a time. So I'll just take this row right here and we'll look at the segment, what it is, what its point of concurrency is, and then we'll do the next one by one. Okay, so down here, first the perpendicular bisector. Now this is actually a huge concept. What is the perpendicular bisector? So it's literally what it says. It's perpendicular and it bisects the sides. So it's perpendicular to a side and it passes through the midpoint. You see the right angle. You see that it passes through the midpoint, so it bisects the side perpendicularly. Here's the big idea before we get to the point of concurrency is this theorem in the book that it gives, and we'll actually prove the forwards, like that if it's on the perpendicular bisector, then it is. We'll prove that a few pages down. But the idea here is the perpendicular bisector is literally exactly the collection of points that are equally distant from A and B. So if you form an isosceles triangle, and then you form a different isosceles triangle, and then you form, like, I don't know, the midpoint too, that's equally distant, and then you do another isosceles triangle from A and B, then all of these points together, infinitely many, create a line, and that line is the perpendicular bisector. So every single point that's equally distant from those endpoints A and B, at least 2-dimensionally on this plane, lies on that line. And every point on that line is equally distant from A and B. Now that's really, really useful. This is cool. Now in 3D space, what you'd have is you'd have 2 points in space A and B, and all the points that are equally distant. Same thing, you get all these isosceles triangles, but the isosceles triangles are now in 3 dimensions, and so what you get is a plane passing through this midpoint area, and every single point on it in 3D space forms an isosceles triangle with it. So that's why I just mentioned in 2D space, it is all the points are equally distant from A and B on that plane. Okay, so then if every point on the perpendicular bisector is equally distant from A and B, well then that means where 2 perpendicular bisectors meet, that means, well, you know, if this point is on this perpendicular bisector, it's equally distant from A and B. So let's call this point X. Well then that means from A to X is the same as from X to B, because it's on the perpendicular bisector of AB. And then a different color here, I don't know, let's do purple. Well, if X is on this perpendicular bisector, well then that means it's equally distant from B, well, XB equals the distance from X to C, and so then you just link those together by the transitive property, and you get that it's equally distant from AX is the same as XB is the same as XC, it's the same distance from all three vertices. So what does that mean then? If it's the same distance from all three vertices, it's those superpowers, then we can always create a circle centered at this point with this radius that is that equal distance to each, and we get, oh, I can't draw an actual circle, but it would look, woo, it's something like that. That's a nice goose egg. Let's try a woo-hoo-hoo. Let's see, come on, there we go. So we could draw a circle there. Now mine isn't perfect because I hand drew it, but we can always draw a circle centered at that point because it's equally distant from the three vertices that passes through the three vertices where that distance, where that distance to the vertice is the radius. Right, so we call this the circumcenter because to circumcenter, it means the center where you can circumscribe. Circumscribe means to draw around. So if I took a rectangle and circumscribed a circle, that means to draw a circle that barely touches. It's the smallest circle that goes around it, right? To circumnavigate the globe means to travel around the globe. So to circumscribe means to write. Scribe means to write. So to circumscribe means to write around and have it barely touch on each side, okay? So its superpower, just going back up here, is you can circumscribe a circle about it. So, I'll try and draw it. Let's see. We can always circumscribe a circle that goes through, I'll make that a little bigger here, and it goes through that point. We'll make that a little bigger. Something like that, where it passes through all 3 points and it has that radius. Oh, that looks better. Okay. Whew. Notice that this point is not always inside the triangle. So in this example here, it is clearly when we have an obtuse triangle, this circle that goes through all 3 points has to look something like this. Ooh, that's not perfect. It would have to be a much larger radius. And then let's move this circle. There, it would look something like that, more or less. And so you'd have it centered around this perpendicular bisector. Again, I'm freehanding all this. That's why it's not lining up perfectly. But that's the idea. So this point doesn't have to lie inside the circle, especially on obtuse triangles, it doesn't. On right triangles, it lies on the triangle, which is interesting. And when we get to circles, we'll kind of see why is that. Okay, I'm going to delete this circle because it's going on to my next page here. All right, so let's talk about the next one. So an angle bisector is analogous to this, except instead of being equally distant from 2 points, these are all the points that are equally distant from the sides of the angle. So now this is a little tricky because we have to first define the distance from a point to line. So if we have a point, the distance to a line, you don't just draw any old line segment in any direction, right? Because then you could say, well, I'm 7 away from this line. No, I'm 6 away from the line. No, I'm 3 away from the line. You can't just make up directions. So if we're going to say what is the distance from a point to a line, the way we do that is we draw the shortest path, which is a perpendicular, and we say this is defined to be the distance from a point to a line. So if I take all the points that are equally distant from these 2 sides, what I end up creating here, just to check, is this point, check if it's equally distant. I draw the perpendicular to this side and the perpendicular to this side. And yes, those are the same distance. This point over here, I draw the perpendicular to each side to check its distance. And I go, oh yeah, look, it is equally distant. And so actually the angle bisector, if you think about it, right, I could think of this as like an isosceles triangle and stand it upright and go, I'm just cutting that isosceles triangle right down the symmetrical side, like right down the line of symmetry down the middle. That's what it is. And so you get everything on the left and right is equal, even this kind of diagonal looking distance here. Okay, so I'll leave it back like this. So then what that means is if you have the 3 angle bisectors meet, so I'm just going to draw it really quick. Ooh, freehanding it. So this looks about maybe angle bisector like that. Okay, and then we'll do angle bisector this one. Looks about, I don't know, there, and then hopefully this angle bisector passes through. Let's see. Oh yeah, that looks pretty good. A little off, but the idea is then this is equally distant from all sides. So in other words, if I draw and I'll take a different color here, maybe like green, I could draw a perpendicular this side, and it's the same distance as the perpendicular this side, and it's the same distance as the perpendicular this side. That's our radius, and we can now draw a circle that just skims each side. So this is called the incenter, because we can draw a circle inside the triangle that just touches. Again, because of those equal distances, that's exactly what a circle is you swing that equal distance around in a circle. So we call this the incenter because we can inscribe, that means write inside, a circle in the triangle. And again, to inscribe something, like we had a pentagon here, we inscribed a circle, that would be like inflate this balloon until you can't inflate it anymore and it just touches each of the sides. That's what it means to inscribe inside, to write inside. And so up here, its superpower is you can inscribe a circle in it. So the point always has to be inside. If you're drawing a circle inside the shape, well, the center of that circle obviously has to be inside the shape. So this point is always inside the triangle, and its superpower is you can inscribe a circle inside because it is equally distant from the sides. Again, it's the perpendicular bisector is equally distant from points, so it is equally distant from all 3 points. The angle bisector, equally distant from the sides of the angle, so it's equally distant from all 3 sides, so that's why you can draw a circle inside. Okay, so it's cool stuff to think about, right? All right, so what about the median? The median's interesting too. So the median, if you think about it, it's defined to connect the midpoint of the other side to a vertex. Okay, now let's just like a kind of slanty line here. But here's the cool thing. You are cutting the area of this thing in half. Now you could think about it like algebraically, like the area of one of these triangles is the same height and yet half of the base. So you have, this is 1/2 of 1/2 base times height. So it's half of the whole triangle's area. Or you could think about it like I take all these slices of a triangle. This is what calculus does. You take slices of a triangle, and in every slice here, half of the line lies on one side and half of the line lies on the other because we have the midpoint of every single segment there. So that's another way to think about it. No matter how you think about it, what you end up getting is half the triangle's areas on each side. So if I had this triangle and I pulled it out of my screen and I held it in my hand, what that means is this line down the middle is its balancing line. We have half of its area, now if it's uniformly dense, so we don't have like a really thick side and a thin side, but if it's all uniformly dense, I could balance the triangle on that line. That's its balancing line, okay? Well then what if we can balance it on that line, and we draw the other median to this side? Then that means we could balance it on that line too. And so if we could balance it in one direction on this line and balance it the other direction on the other line, what that means is if you just put your pen tip right there on that point and removed everything else, it would balance on that very spot in space. It's its balancing point. So there's a couple different ways to think about this. One, it's actually the mathematical average of the points. So if you average up the infinitely many points in that triangle using calculus, the average of all those points is the centroid. Okay? Now, another way to think about it is if you want to find the centroid, you literally take the 3 points here, x1, y1, x2, y2, x3, y3, and you just add them up. You go to the centroid's point. This doesn't come up that often, but the centroid's point is actually x1 plus x2 plus x3 divided by 3, and y1 plus y2 plus y3 divided by 3. Again, that's part of why it's a balancing point. It is the average of all the points. Half is on one side, half is on the other, but in multiple dimensions. So any way you slice it, you get this half on one side, half on the other, as long as that slice goes through the centroid. Now, the useful thing that we use is, and this is only useful because the book asks a question specifically asking this, is the centroid cuts the median into these 2 pieces. So if I have these 3 medians meeting, right? Again, a median is vertex to midpoint. Where 2 of them meet, cuts this one median into 2 parts. Now you could think about it in 2 ways. The ratio of the 2 parts is 2 to 1. That means this one on the left here is twice as long, 10, as this one is 5. That's a 2 to 1 ratio. Or another way to think about it is it's in a 1/3 and 2/3 of the whole thing. So if this is 10 and 5, that's because 10 is 2/3 of the whole 15. And the 5 is 1/3 of the whole 15. Or you could think of a 2-to-1 ratio as literally saying 2 parts is on one side, 1 part's on the other. There's a total of 2 parts. Or you could just say divide both sides of this ratio by 3. 2/3 to 1/3 is still a 2-to-1 ratio. So however you slice it, that's a trick that gets used a lot, like algebraically on book questions, chapter review, quizzes, tests. It's just common that where the midpoints intersect the centroid, that cuts these into 2-to-1 ratio. And it's for all of them. So I wrote it for these. So here's some multiple of a 2-to-1 ratio. Here's a different multiple of a 2-to-1 ratio. And then here's even another one. So 2c and 1c here. Okay. Last one here is the altitude. So the altitude meets at this point called the orthocenters. Nothing special about it. So just altitudes. Okay, so the altitude is really the height of a triangle. You've been doing this in middle school. So the altitude can lie inside, outside, or on a triangle. So in an acute triangle, the altitude or height of the triangle is inside. In an obtuse triangle, we extend a side and drop it down. So, I mean, there's always 3 altitudes, right? So that one's outside. This one is inside. And then if we try and draw this one perpendicular to this side, you go, how do you do that? Well, again, you extend the side and then go, oh, here is that other altitude. So there's always 3 altitudes. And then in a right triangle, obviously, this side is perpendicular to the other side, so it's an altitude. So actually, here's like altitude 1, here's altitude 2, and then the third altitude is right here. And this is actually a pretty cool problem later on. When we get into similar triangles, we'll look at this right triangle altitude problem a lot more. Okay, and there's nothing special about it, but the point can lie outside. Specifically, that's an obtuse triangle. Interestingly, if we're on a right triangle, this vertex right here is the orthocenter. Yeah, interesting. Okay, interesting. So that's it. So usually all these segments are different. So in a scalene triangle, the median and the angle bisector are totally different segments, right? They're not the same. Perpendicular bisector, that's a totally different segment. However, if any 2 of them are the same, so if the angle bisector is the same as the median, any 2 of the 4 are the same, that actually means all 4 are the same because you have an isosceles triangle. So for example, I drew this triangle and said, what if we have AD here and it's both the angle bisector and it's the altitude? I just picked 2 randomly. So the angle bisector would be these 2 angles are the same. And then the altitude would mean this is a perpendicular angle here. It's not the perpendicular bisector. The hard part about perpendicular bisector is you don't know it goes through the vertex, because a perpendicular bisector just goes off willy-nilly, bisecting the side and perpendicular. Proving that it passes through its point is a little hard. That's actually a medium difficulty proof for sure, and we have to do it in a special way we're not going to talk about. All right, so anyways, if we have this as the angle bisector and the altitude, well, look at this. This side's congruent to itself by reflexive property. And so this triangle on the left, ASA, is the same as triangle on the right, ASA. So then by CBCTC, these must be congruent. So see, if you have 2 of these are the same, then what you know is this is an isosceles triangle, and everything over here is everything over here. And so yeah, this is necessarily congruent. So it's also the perpendicular bisector, AD is, and it's also, what's the third one? Oh, median. It also connects the midpoint, so it's also the median. So as soon as you have it's 2 of them, it's actually all 4 segments: perpendicular bisector, angle bisector, altitude, and median. So that's an interesting case. All right, let's just do some homework problems now. Draw a triangle in which the circumcenter lies outside. So now we got to think, what's the circumcenter? So the circumcenter is when you draw a circle outside. That means it's equally distant from all the vertices, so it can do that. And so what that means is that equally distant from the vertices, that's that perpendicular bisector. So that's all the points that are equally distant from the endpoints. So this is where you do the perpendicular bisector. So when would the perpendicular bisectors meet outside the triangle? Well, for either the orthocenter or the circumcenter, that happens when it's an obtuse triangle. And so the perpendicular bisector of this one and the perpendicular bisector, again, just freehanding it, of this one meet somewhere around here. And the perpendicular bisector of this one 1, 2, 3 is congruent to 1, 2, 3, and this is a right angle. They all meet about there, and the circle would look something like that. So that would be an example. It would be an obtuse triangles when the circumcenter would lie outside of the triangle. Number 3 says, find a counterexample to this, and it says, an altitude and an angle bisector are never the same segment. Well, we just did that exactly. Is it altitude and angle bisector? Oh, here's our counterexample right here. But the idea is either an isosceles triangle or a special or special one, which is equilateral triangle. A special or special, that's good. So equilateral triangle. So either one of those, this segment down the middle, that line of symmetry, is going to be both the angle bisector and the altitude, and it's the midpoint of the bottom, so it's the median, and so then it's also the perpendicular bisector. So all 4 are going to be the same whenever you have even one line of symmetry, let alone 3 lines of symmetry in an equilateral triangle. Okay, so what about next? What about a proof? Okay, so CD is the perpendicular bisector of AB. E is a point on CD. Oh, so if we just connect to these and we say, oh, so these were the given, well, then that means that the distance to the endpoints of AB are the same. So that means AB is, and we could do equal or congruent. I'm okay with either one. Well, AB, that's not what I meant. The distance from A to E is the same thing as the distance from E to B, because that was our very, oh wait, this is what we're trying to prove. I'm sorry. So this is the theorem we're trying to prove. So we can't assume that. It's saying, can you prove theorem 5.1 that says that? Oh, okay, then let's do that. So how are we going to prove 2 things are the same? So what I'm going to do first is I'm just going to draw EB and EA. And what lets us do that? That's between any 2 points is a line. Exists exactly one line. Okay, now that we drew that, what can we do? Can we show at all these triangles are congruent? Because that's how we pretty much show anything is congruent or equal in geometry. So I'm guessing we're going to try and show this triangle and this triangle are the same. So let's see if we can do that. Well, we have, this is the perpendicular bisector. So if it's the perpendicular bisector, that means we have this angle is a right angle, and we have this is congruent to this. Okay, so let's start with that. So we know CD is perpendicular bisector AB. All right, so that tells us that AD is congruent to DB, right? That's one part of, that's the definition of the bisect part. And then it also tells us that angle ADC, or ADE, it doesn't matter what you name it, so let's call it ADE since we're in that triangle, is a right angle. And I'm going to move this over a little bit. And we'll draw this line. Okay. It also tells us that the other angle is a right angle too. So let's move this one into the middle. And so now we've got angle, what's the other one? BDE. BDE is a right angle. Okay, so if these are both right angles, and that's by the very definition of perpendicular lines, or you could say by the definition of perpendicular bisector, but it's really the definition of the perpendicular lines. Okay, so now we've got that. We'll move this over a little bit. Well, if those are both right angles, well, then they're the same as each other, right? Because all right angles are congruent. That's a theorem we've used. That's a theorem, or proved. That's a theorem that we will see come up again and again. It'll just be an easy thing to reuse. So all right angles congruent. Okay, so we got those angles and those sides are the same. Is there anything else? Oh, well, look at this. This side is shared between the 2 triangles. So we also know, and I'm just going to bring this down a little bit because we're going to use that. And I'm going to just go like this. And then we're going to bring in now, we're going to say, well, I also know that side ED is congruent to itself, ED, right? And that's by reflexive prop congruence. And now with those the same, well, that gives us side angle side, right? That gives us, just zooming in, that gives us a side and another side, and the angle between is the same as the other triangle. So that's side angle side. Let's go down here, and we say by side angle side, triangle is congruent to triangle. We need to get the order right. Okay, let's go up here. I'm going to go from 1 to right angle to 2. That's ADE. 1 right angle 2, BD. Okay, so ADE, BDE. All right, and what we're trying to show is that this length is the same as this length, EB to EA. And so E to A and E to B. So we can say that E to B is congruent to E to A, right? That's by CPCTC. Anytime you have triangles that are congruent, then all their parts are congruent, or all their corresponding parts, that is. And so then that tells you that the distance EB is the same as the distance EA, and that's by the very definition of congruent segments. Perfect. Okay, good proof. All right, so now let's do a couple algebra problems. So it says these lines are perpendicular bisectors. Okay, so we're doing a lot of perpendicular bisectors of PQ and meet at T. So these are all perpendicular bisectors. Again, what was that theorem we just did? If they're the perpendicular bisector, then they're equally distant from the endpoints of whatever they were the perpendicular bisector of. So every point on the bisector equally distant from A and B. Well, down here, if these are the perpendicular bisectors, then that means this length to that point on the perpendicular bisector is the same as this length. So that means 2x equals 8. Okay, let's see what else we could find before we just go ahead and solve. Well, that also means, right, that point is equally distant from all 3 vertices. So just like we said that, it's also the same distance as here. So we know that 8 equals 3y minus 1. And we could even say that 2x equals 3y minus 1. We don't need to. But it's also the perpendicular bisector. So if it's the perpendicular bisector, it's perpendicular to and bisecting the bottom side. So that means z plus 4 is equal to 7 because the perpendicular bisector goes through the midpoint of the bottom side. Okay, so there we go. So this one up here, not so useful, but the other one's very useful. This one means x equals 4. Here we add the 1, we get 9 equals 3y, so y is 3. Down here we subtract the 4, we get z is 3. We could plug these back in. We get this is 8, good. We get this is 8, good. We get this is 7, good. All worked out. Okay, always, sometimes, or never. Yes, good job, pass me for putting this problem in here. I like it. Okay, the 3 medians of a triangle intersect at a point in the interior. Well, think about what a median is. It says connect the vertex to the midpoint of the other side. So even if we had some extreme thing, we're connecting to the midpoint and we're traveling from this vertex. So there's no way to like go outside, because if we go outside at all, it's going to keep going outside and it would never come back inside. So yeah, 3 medians would always meet on the inside. Another way to say it is the 3 medians meet at the centroid. And what is the centroid? The centroid's a balancing point of the triangle. And so can we have the balancing point of a triangle be outside the triangle? That would be crazy. Try and hold up your pen and lay a triangle on the side and just watch it fall onto the floor. Be like, nope, I did an experiment. That balancing point outside the triangle did not work. Oh, I cracked myself up. Okay, so that first one that one's going to be it's always true. Okay, whoa, I did a terrible job erasing there. Okay, so I'm just going to put an A there. That's always true. The second one, 3 altitudes intersect at the vertex of the triangle. Well, that was a special case we looked at. So really the difference is acute, right, and obtuse. And so if it's a right triangle, then this is an altitude, and this is an altitude, and then the third altitude is right here, and yeah, they all meet there. So at least once. And then here we have an altitude, we have an altitude, and we have an altitude. So no, that time it did not. And then when we have an obtuse triangle, we have to extend this side to draw the altitude. And we have to extend this side to draw this altitude. And then this altitude we just draw right through the middle. You go, where do those intersect? Well, you have to continue them down here. And they all intersect down there somewhere. And so this one would be sometimes. And specifically when it's a right triangle, that's when it would lie on the vertex. And any other time it would not. Okay, the three angle bisectors of a triangle intersect at a point in the exterior of a triangle. Well, let's look at it. So we bisect this angle. Well, the bisecting of the angle has to be between the sides. So that's between the sides. This one is between the sides. So how could they possibly meet outside the triangle? So I'm already thinking totally impossible. Another thing you can think about is they meet in the incenter, and the incenter's ability is we can inscribe a circle. So we can draw a circle inside. So if we can draw a circle inside centered at this point, can that point be outside the triangle? No, totally not. So that is definitely a never. They could never be in the exterior. I mean, the angle bisector can continue outside, but it will never hit the angle bisector of this one that continued outside. It'll only hit it inside this shape. Okay, last one here. The three perpendicular bisectors of a triangle intersect at a point in the exterior of the triangle. Oh, this is the same as the other one. So if we do perpendicular bisectors, the interesting ones are if we have a right triangle. This is something we'll talk about in a later chapter, so you don't need to figure this out so much right now. But the two perpendicular bisectors will actually meet on the triangle. If we have an acute triangle, then the perpendicular bisectors will meet inside the triangle. And if we have an obtuse triangle, woof, that was pretty bad. If we have that, then this will be meeting outside. So yeah, it can meet on the triangle, inside or outside. So it says three perpendicular bisectors meet in the exterior, so that's sometimes true. Oh, I love those problems. Okay, so here's the classic problem, right? So it's a centroid. So then solve for these. Well, remember the centroids thing is it cuts these into a 2-to-1 ratio. Oh, that's funny. It's a 10, just like my example was before. So it cuts these into a 2-to-3 ratio. So here's a 2-to-1 ratio. So we're at 2 out of 3 total parts. And so you would go the ratio of 10 to 4y minus 2 is a ratio of 2-to-1. Or you could just write an equation saying take the smaller thing, 4y minus 2, and multiply the smaller thing by 2, and you get the bigger thing, right? That's an easy way to think about it. And so now we go, okay, well, what does that mean then? Let's look. That means we got 10 equals, or let's just divide by 2 actually. So we get 5 equals 4y minus 2. Let's add the 2. We get 4y equals 7. Divide, we get y equals 4/7. Okay. Now let's see if we can find x. Well, look at this. This line here goes through this point and through this point. And so if it goes through this point and this point, then it's called the median. That's what makes the centroid, is all the medians. And so that means that this is the midpoint, right? The medians that create the centroid just connect the vertex to the midpoint. And so we know that 2x minus 4 equals x. And so when we subtract x, we get 1x over here. We add the 4, we get x equals 4. Plug that back in just to double check. That's 8 minus 4 is 4. And on the right is 4. So yeah, that works. Okay, so we got x equals 4. We got y equals 4/7. And now how can we get z? Now this is crazy. There's nothing over here. Well, if you didn't read the given, then there wouldn't be. Okay, so let's do this last one then. So it says the whole length of this segment is 24. And this segment over here is z. And this is the longer one. So this is 2/3 of it. This is the 1/3 portion. So how could you solve this? I mean, one way is just 1/3 of 24 is equal to z. And so z is equal to 8. That's a pretty straightforward way. Now, the most common error here is people get mixed up with multiplying by 2 or dividing by 2 or multiplying by half, things like that. The easy way I remember it is I imagine having a tall, skinny triangle, and I connect the midpoint here with the midpoint here. And it's obvious to me that this is the longer portion and this is the shorter portion. Another way I think about it is that these two sides have equal area, and this is tall and skinny, and this is short and wide. And so the short and wide one is the 1/3, and the tall and skinny is the 2/3. But that's my way of remembering which one's the 1/3, which one's the 2/3. Okay, now let's do some coordinate geometry. This is a pretty common one. where they say, okay, here's 3 points. Find the... Now, the centroid, the shortcut would be just average. So take all the x's, add them up, and divide by 3. And then we'll go all the y's, add it up, and divide by 3. Now, let's say we didn't know that, though. Let's say we just want to do it with a brute force knowledge, okay? Well, what the centroid is we have to find the midpoint of 2 sides. I mean, you could find the midpoint of all 3 sides. So the midpoint's easy. You just add them up and average them. So the midpoint here is you add up these 2, and the average is 2. Add up the 6 and the 0 and divide by 2. So the average there, the midpoint is 2, 3. And then let's find, I don't know, the midpoint of this side over here for no reason. So the midpoint there is -1, comma, 4 of us, so 5. So that's the midpoint. So now all we need to do then is say, where do these 2 lines intersect? Okay, so we need to write the equations of those lines really quick. All right, so I'm going to call this one L and this one M. No, not M, because then we have weird confusion. Okay, so if we want to find L, okay, well, we're going from -2, 4 to 2, 3. Okay, so that means our slope is, we went down 1 over, and then we went up 4. So our slope is -1/4. I'm just going to plug it in right now. So the equation of that line then, using point slope right here, is y minus 3 equals -1/4 times x minus 2. Okay, so that's the equation of that line. The line P, again, I got to find the slope here. So our 2 points are -1, 5 and 4, 0. Whoa, I drew multiple things there. 4, 0. Okay, so the slope then is we went down -5y, and then we went up 5 there, right, from -1 up to 4. So the slope of this was -1. So then I'm just going to use, I don't know, these 2 points and write the equation of the line. So we have y minus 0 equals -1 times x minus 4. And so the equation of that line is y equals -x plus 4. That looks right. It looks like it goes through 4 there. Okay, so we have that equation. And I'll rewrite the first one too. So this is -1/4 x and then plus 1/2. And then I'll just add the 3. So we get y equals -1/4 x and then plus, and now we had 1/2 and we added 3, so we get 7/2. Okay, so to find out where 2 lines intersect, that's a system of equations. So the system of equations here are these 2. Well, the easiest is substitution here. We already have this equation is equal to y, and this equation is equal to y. So then to find centroid, I just go -1/4 x plus 7/2 equals -x plus 4. So I'll add this up, or actually let's just multiply by 4 on both sides. So we get -x plus 14 equals -4x plus 16. So we add the 4x to the left, we get 3x. We subtract the 14 from the other side, equals 2. And so we get x equals 2/3. And then all we do is plug it back in anywhere. I'll plug it back into this one because it looks easier. So then y is equal to -2/3 plus 4. And so we get y equals, that's 12/3. That's what 4 is. And so 12/3 minus 2/3, we get y equals 10/3. And so the centroid is at 2/3, 10/3. Now let's do it the other way just to double check that we got it right. And so up here, I'm going to add up the 3 black points here. So we get -2 plus 0 plus 4 over 3. And then we get over here 4 plus 6 plus 0 over 3. And what we end up getting is 2/3, 10/3. Oh yes, that was shorter. Okay. But I like this using the algebra to do it. I'm actually going to have to add another page here as I've solved for each of these algebraically. But I just want to show you, like, don't be scared of getting into the algebra. Algebra is by far your bread and butter moving forward in every math class, so don't avoid it. I mean, yeah, cool, clever, elegant tricks are useful, but that's just a one-off maybe. Now be adaptable, but don't be scared to just fall back on it. Okay, so I'm going to erase some stuff in this picture here. So the orthocenter and the circumcenter. Actually, you know what? I'm going to leave the midpoints, because I'm going to use those for the circumcenter. So the circumcenter here, remember what that is, okay? The circumcenter, I can draw a circle around the outside because it's equally distant from the vertices. So what points are equally distant from those vertices? Those are the perpendicular bisectors. So I already have the midpoints drawn. So what I'm going to do is just get rid of, these blue lines here. And what I need is I need to find the perpendicular bisectors. So the two perpendicular lines passing through the midpoints. Okay, well, I can do that. So I'll switch over to pink here. So perpendicular line passing through here, perpendicular line passing through here. So what I have is, let's call this one L and this one P. Okay, so L is perpendicular to, and then the line between 0, 6 and 4, 0. But it passes through point, the midpoint, which is 2, 3. Okay, and then P, separately, is perpendicular to the line between -2, 4 and 0, 6. And it passes through the point, midpoint, -1, 5. Okay, so now all I need to do is find the equations of these lines and see where they intersect. All right, well, let's do it. Okay, so perpendicular to this slope. Well, this slope is down 6 and then up 4. So this slope was -3 over 2. So the new slope is positive 2/3. Okay, so here's one equation, and I'll write it out in a second. And then the other equation, okay, so the old slope was, we went up 2y, and we went up 2x. Oh, that's nice. That's just a slope of 1. So our perpendicular slope is -1. Okay, great. So those are our two equations here. Let's write them out. So for L, we have y minus 2 equals 2/3 x minus, oh, I wrote it wrong. I do that sometimes, reverse the order. So it was y minus the y value equals slope, and then x minus the x value. And then over here, the other one is y minus y value equals slope, x minus x value. Okay, so now I'm just going to rearrange these and then do a system of equations here. So this is y minus 3 equals 2/3 x. Oh, I was supposed to distribute that. 2/3 x minus 4/3, right? Yep. And then we add the 3, so we get y equals 2/3 x. And now if we add 3, 3 is 9/3, and so that's plus 5/3. Okay, then over here it's y minus 5 equals, so this was already x plus 1. Then we distribute the negative, so we get -x minus 1. We add the 5 to both sides, and we get y equals -x plus 4. Now we system of equations that thing, so we can just substitute. They're both equal to y, so transitive property, they're equal to each other. 2/3 x plus 5/3 equals -x plus 4. Let's multiply both sides by 3. 2x plus 5 equals -3x plus 12. Let's add the 3x to both sides. Let's subtract the 5 from both sides, and we get 5x equals 7. Oh, that's no fun. X equals 7/5. And now we just have to go back and plug that in. Let's plug that in right here because that's easy. So then y equals, oh, and I didn't label this up here. This was the centroid. Okay, now we're looking for the circumcenter. So we just plug that right in here. So we get -7/5 plus 4. Now 4 in terms of fifths, that's 20/5. And so y is equal to 13/5. Woo, crazy problem. So then the circumcenter is equal to 7/5, 13/5. Okay, and then let's go one more. So the orthocenter, that's the perpendicular. So there we have the same idea of finding the two perpendicular lines and where they intersect, except in this case, we have the perpendicular line, but passing through the vertex of the other side. So since we already did the slopes here, what I'm going to do is I'm going to reuse that work. So I'm going to switch over to green, and I'm going to say, so perpendicular to 0, 4, or 4, 0, and 0, 6. So perpendicular to this line, but now passing through the vertex, right here. So I'm going to go to the next one. I'm going to go perpendicular to a slope of negative 3 over 2. So we have the slope already. So our first line has a slope of positive 2/3. But now it passes through the point negative 2, 4. All right, and then our other one, we have, again, it's perpendicular to this line. And we have that slope, so it's perpendicular to the slope of 1. So it has a slope of negative 1. We know that. The only difference is, instead of passing through this midpoint, negative 1, 5, it's perpendicular to the side, but it passes through 4, 0. Okay, so it passes through 4, 0. So it's perpendicular to the side, passing through the other vertex. Let's go ahead and solve it. So here we get two equations. The first one is y minus 4 equals 2/3 times x minus negative 2. The second one is y minus 0 equals negative 1 times x minus 4. So we get y minus 4 equals 2/3 x plus, and this was plus 2, then we multiply it, so it's plus 4/3. And then over here we get y equals negative x plus 4. And then, I can get this to be y equals by adding the 4. So 2/3 x plus, and if we add 4, in terms of thirds, that's 12/3 we're adding. So we get plus 16/3. And now we get system of equations. Where do these two lines intersect? We get 2/3 x plus 16/3 equals negative x plus 4. Multiplying by 3, 2x plus 16 is negative 3x plus 12. Adding the 3x, we get 5x here. Subtracting the 16, we get a negative 4. So we get 7x equals negative 4. X is negative 4/7. I almost wrote thirds. Okay, and then we just plug that in. Again, I think the easiest one to plug it in for is right here. So we get y equals negative 4/7 plus 4. So that's positive 4/7 plus, and I'm going to convert this 4 into 28/7. And so we get 32/7. Whew, that is brutal. So that means the orthocenter, where the three altitudes meet, is at negative 4/7, 32/7. So I maybe went too fast there, but that was a long problem. I just wanted to show you, don't be afraid of the algebra. You can absolutely find where two lines intersect. Okay, that's called a system of equations. Now let's just finish with two proofs, and that's it. Okay, so this is an isosceles, with this being the vertex angle, which means these are the two congruent sides. Base angle theorem says these angles are the same. That's stuff we know. We haven't written it in the proof yet, but I'm just kind of reasoning through what we'll do. YV is the bisector of UV, so that means this angle is the same as this angle. That's the angle bisector. And this angle is congruent to itself by reflexive property, and we want to show that YV is the median. So how do we show that YV is the median? Well, V is already the vertex, and what is the median? It connects the vertex to the midpoint, so all we need to do is show Y is the midpoint. So to go to the end of the proof here, if we want to show YV is median, that would be the only way to get to a word is by the definition of the median, right? And then to get there, what we really need to show is Y is the midpoint of the side. So what side is that? That's UW. That's the only way to get there, right? That's what the definition of a median is. And the only way to get to a midpoint is to say the definition of a midpoint. And so how could we get that Y is the midpoint? Well, what's the meaning of that? That just means that from U to Y is congruent to from Y to U, or Y to W. So if Y is the if those two segments are congruent, right? If this piece and this piece are the same, well then Y is the midpoint, and then that thing is the median. So just working backwards, we want to get there. And how do we show two segments are congruent? Why, we always do that, not always, but most of the time we do that by two triangles are congruent, right? So what we're trying to do is show two triangles are congruent, and we have more than enough information here. Okay, so let's see. I'm going to choose side angle side, or angle side angle. Let's do side angle side here, and we'll use reflexive property. Now, we haven't used base angle theorem that much. Let's do base angle, definition, and definition. Okay, let's do that. So we'll start with triangle UVW is isosceles. I'm not going to write out the whole thing with which is the vertex angle, and that was given. And so that tells us that side UV, picture's getting messy, is congruent to side VW. Okay, that's by the very definition of an isosceles triangle. All right, and then what I'm going to do now is I'm going to sidestep, because if I go down, I'm kind of blocking my path. And I'm going to use that thing right there to prove the triangles are congruent. So just to clean up this picture a little bit, what I want to do now is use the fact that these sides are congruent to say these angles are congruent. So I can say to the side here, that means that angle U is congruent to angle W, and that's by the base angle biconditional or the base angle theorem, whichever. I like just saying biconditional, so we have the forwards and the backwards. Okay, so now we have that angle's congruent and that side's congruent. That's two of the pieces, right? Okay, now we just need something else. Well, again, we were giving that it was the angle bisector, so up here we know that YV is angle bisector of UVW. That was given to us. And if that was given, well, the very definition of that is that angle UVY is congruent to angle UVY WVY. That's not a V, WVY. And that's by the very definition of an angle bisector. Okay, and so we had more than enough information. You could have proved this a different way, but given that I now have this angle, and what do I have? So look at the two triangles. I now have two angles and the side between. Matches two angles and the side between. So that means two A's with an S in the middle. That's ASA, triangle congruence. And then we just go to the ordering. And I'm going to go one angle, two angle, none. So one angle, two angle, none. That's UVY is congruent to WVY. And then let's check the order. Does that mean U to Y, 1 to 3, is W to Y? Yes, it does. And that's by CPCTC. And then that means that it's the midpoint, and then that means it's the median. Cool proof. Okay, last one here. Write a two-column proof. Flowchart. Okay, XY is the same. So we have this whole side is the same as this whole side. Again, we could use the base angle conditional there. Okay, biconditional. Then YM, and those are median. So what does it mean to be a median? That means it cuts this and this into congruent parts, and it cuts this and this into congruent parts. Okay, but since these two sides are the same, actually, we don't need different markings. It's actually going to be that these are the same, right? Okay, so this might take some algebra here. And then what do we have? Well, we know that this side's congruent to itself. We know that base angles are congruent by the base angle biconditional. So all we really need, if we want to show YM, where's YM? If we want to show this side is congruent to this side, then the way we're going to do that, as usual, is congruent triangle. So all we need to do, and I'll draw it in pink here, is we need to do that this triangle here is congruent to this triangle here, and we have almost all the information we need. Okay, what we need to do now, though, is we need to say, okay, well, if YM is median, and I'm going to just copy this and change the letters, so I'm going to do it. So that means that M, whoops, not line segment M, is midpoint of ZX. Okay, and that's by the definition of median. And so that tells us that X to M and M to Z are the same. Okay, that's by the very definition of a midpoint. And now we're going to do the exact same thing. So I'm just going to take that and I'm going to copy it. And I'm going to paste it over here. And we're just going to change some letters. Okay, so that means, so ZN, and just all I'm going to do is change the letters, but all the reasons are still the same. So we have ZN is a median, which tells us that N is the midpoint of XY, which tells us that from X to N and from N to Y are the same. Okay, so what we want to do, though, is we want to get NZ and NY are equal. Okay, well, here's what we can do. Okay, let's bring these down a little bit. Well, then that means that XM is the same as MZ, All right, and that also means that xn is equal to ny. Okay, that's by definition of congruent segments. Now there's a shorter way to do this with a theorem that we did in the past, but I just want to do it ourselves. Okay, the shorter way is that when you have a midpoint, it's equal to half the whole length. That was a little theorem we proved just to save us from this algebra. I don't want to get saved from the algebra. Let's dig into the algebra right now. So now we need to use the fact that this is an isosceles triangle. XY is equal to, okay? So first, let's say that since they're between, we're going to go ZM and MX. So ZM plus MX is equal to the whole ZX. That's the segment addition postulate. And then over here, we're going to do the same thing. We're going to say, oh yeah, and by the way, XN plus NY is equal to the whole XY. That's segment addition postulate. Okay, well then we can combine these, and actually, which segment do we want to keep? We want to keep NY and MZ. So we want to keep MZ and we want to keep NY. So what that means is, what we have is NY, and we sub this in, so we have NY plus NY. So we have two of these is equal to XY. Okay, that was substitution. And over here, we have the same thing. We want to keep the MZ or the ZM, so we're going to go ZM plus ZM is equal to ZX. Okay, again, those are both substitution property of equality. Substitution, okay, prop equality. All right, so now that we've got that, we're going to bring in this top fact here. Well, we're going to say XY is congruent to ZX. That was given to us, okay? And that means that it's equal. So XY is equal to ZX. Okay, that's the definition of congruent segments. All right, so then we put this together, and using substitution or transitive twice, we end up getting ZM plus ZM is equal to NY plus NY. And that was substitution. Prop equality. Now, I'm just going to say we use algebra, but you could say this was division, property of equality, but that means ZM is equal to NY, which means that ZM is congruent to NY. That's what we wanted. Yes, okay. So I'm going to say this was using algebra, and this was definition of congruent segments. All right, so finally, now that we got that, we can just use the givens, okay? So I'm going to reuse this thing here, and I'm going to say because these two sides of the triangle were the same, then I also know that the base angles are the same. So XZY, so angle XZY is congruent to angle XYZ. Those two base angles must be congruent, and that's why that's the base angle biconditional. Okay, and now what other piece of information do we have? So let's just look at this picture now. What we have is, let's do pink. We have this base angle is the same on left and right. We have this segment was the hard part, is the same as this. And between these two triangles, what else do they have in common? They share this side. So over here we just say, and by the way, ZY is congruent to ZY. That's just the reflexive property of equality. Nope, of congruence, crazy town. All right, so now the question is, where are we trying to go with this, right? We got so dug in there. We're going to try and prove these triangles are congruent because we want to show YM and NZ are the same. So there we go. It's just going to be CPCTC. So we're going to take these two together and say that means the two triangles are congruent by, so let's go triangle, congruent to triangle. Let's check the order. So up here, let's go one side, two side, and one side, two side. That's by side angle side. We have a side and a side with the angle between. So side angle side, MZY, and NYZ. That was SAS, triangle congruence. And lastly, last thing here is CPCTC. We were trying to show that side YM and ZN are the same. So YM is congruent to Zn. We check the order there. Z to N, Y to M. Yes, they are. And that's by CPCTC. Whew! What a proof. I hope you guys enjoyed it. Good luck.